So welcome back. Now my topic is describing function. So what is describing function? Before I derive the describing function, let me define the describing function and what is it. First of all, you must have you have used for various cases transfer function. Now the definition of transfer function is the ratio between output by input when in the Laplace domain when initial conditions are 0. So while defining the transfer function, there are two conditions. First condition that output and input should be in the S domain, and initial condition must be 0. Now so to get the transfer function, you have to apply Laplace transform because output by input in S domain means you have to apply Laplace transform. Now Laplace transform can only be used for the linear system. Now we are dealing with nonlinear element, nonlinear system. Now we have various types of nonlinearities. Now how to find out a function which will represent this kind of nonlinearities. Now transfer function is basically a representation of linear system. Now what about the nonlinear system? In such case, describing function is the ratio between output by input, like transfer function, but not in the S domain. Okay, this is the ratio between output by input. Basically this is the ratio of complex ratio of output to input. Now what do you mean by complex ratio of output by input? The complex ratio of output by input means that the ratio between amplitude of the fundamental component of the output and the amplitude of the input, and with their phase shift between input and output. Now you are not getting, I hope that you are not getting what I am saying. Okay, so basically one thing I must say that describing function is required to describe the nonlinear system. Now this is again a function like transfer function, which is also ratio between output by input. However, there are there are different condition here, and there are different type of derivation here. Now describing function, if what to say about describing function. Describing function is a method. It's a method. It's sometimes it's also called describing function method. You can use for determining the stability of the nonlinear system. Now before you determine the stability of nonlinear system using describing function method, you have to derive the describing function. You have to derive the describing function for various types of nonlinearities, and there is a technique, and you have to learn this technique, that how to derive the describing function for various types of nonlinearity. Now describing function is an approximation method. Okay, and this is a method which is used in those cases where device characteristics deviates by a large amount from the linear operation. So I can also say that the describing function method is not based on a very solid mathematical basis. It is also there is also limitation that this method is applicable for only the systems where low pass filter is there. So another important point of describing function is that it's a frequency response method. Now first of all, I will draw a diagram. I will draw a closed loop block diagram. Now see as I've already said to you that various types of nonlinearity, saturation nonlinearity, dead zone nonlinearity, which are actually present in all practical system. In this block diagram, you see this block is representing a nonlinear element, and the nonlinear element nonlinear element is just placed before the planned transfer function. Now this is if I omit this board block, what will happen? The rest of the diagram is very familiar to you, because you are applying input. There is a plan in the forward path, and the feedback path. There is a feedback path transfer function, which is HS. Now, the plan transfer function and the feedback path transfer function are in the S domain, but this block is, since it is it is the block is representing a nonlinear element, and nonlinear element cannot be expressed in S domain. So what is the, how do I, and this plan and the feedback is represented using a transfer function, which is GS and HS respectively. But what about the non-linear element? Non-linear element cannot be expressed in S domain, because we cannot apply Laplace transform, as I have already explained. So what I can do, I can find out the describing function of the non-linear element. Then I can analyze the system as a whole. Now, input to the what is the input to this nonlinear element? I assume this is xt, and output of the nonlinear element I assume which is yt. Now capital N is required to denote the describing function for the various types of nonlinearity. Suppose it is a saturation type of, suppose there is a saturation type of nonlinearity present in this block, or maybe dead zone type of nonlinearity present in this block. Then n can be derived. N is basically, n denotes the describing function. Like in case of GS and HS, which are basically representing the transfer function, capital N denotes the describing function. So you can find out the n, which is the describing function for dead zone nonlinearity. You can find out the n, which is the describing function for the saturation nonlinearity. You can find out describing function for all types of nonlinearity. And one thing you see that for this n block, which is a nonlinear element, and capital N is used to denote the describing function of a particular nonlinear element. The there is an input applied to the nonlinear element, which is xt, and the output of the nonlinear element, which is yt. Now previously we have seen, when we studied the characteristics curve, the characteristics curve basically denotes also the nonlinear element, and where the input is basically x-axis and output basically y-axis. So this xt is the input axis and yt is the output axis. So if you represent any non-linear element by a characteristics curve, that indicates that x is the input or yt is the output. In this case also, in the block diagram, xt is my input to the non-linear element and yt is the output from the non-linear element. Now what is n? What is describing function? Uh, as I have already given the definition of describing function, I am again repeating my definition of describing function. Describing function of a nonlinear element is defined to be the complex ratio of the fundamental component of the output to the input. Now question is that, again I let you draw this block separately. Now say this is xt, right? So x is xt, and I just am applying a sinusoidal input with amplitude to capital X and frequency omega to the nonlinear element. What will be the output of the nonlinear element? See, input is xt, which is a sinusoidal in nature, and the sinusoidal function is having x amplitude and omega is the frequency. Now what is your expectation from the nonlinear block? In case of linear system, when you studied Bode plot, Nyquist plot, in case of frequency response analysis, the concept was that when you apply a sinusoidal input to the system, the output to the linear system will also provide you the sinusoidal output. However, the amplitude and phase will be different. But if your input is sinusoidal, the output is also sinusoidal for linear system. And that's why in case of Bode plot, for magnitude versus frequency and phase angle versus frequency, the common axis was frequency, because frequency was not changed. Only the magnitude and the phase angle is changed. Now, in case of non-linear element, if you apply a sinusoidal input to the now it is not linear. So if it is non-linear, if you apply a sinusoidal input of amplitude capital X and frequency omega A, the output of the non-linear element is not sinusoidal, but it may be periodical. It will be periodical, but it is not sinusoidal. Not necessarily it is sinusoidal. Uh, it may provide, suppose you are applying sinusoidal input, it may provide square wave periodical waveform. If you are applying sinusoidal input, it may provide triangular type of periodical waveform. It may provide various types of periodical waveform. The output waveform of the nonlinear element is not sinusoidal. What I want to say, it must be periodical, but it is not sinusoidal. Now, what is the type of the shape of the output waveform of the nonlinearity depends on the type of the nonlinearity. If it is a saturation type of nonlinearity, then output waveform may be different shape of different shape. If it is a dead zone nonlinearity, then the output waveform of different shape. If it is a dead zone on-off with dead zone nonlinearity, then the output waveform is of different shape. If it is a backlash nonlinearity, then the output waveform of the nonlinearity is of different shape. So the shape of the waveform of the output from the nonlinearity is different. It depends on the type of nonlinearity. But if you apply sinusoidal input, the output shape may be different, but that must be periodical. And for any periodical waveform, you can apply the concept of Fourier series to find out the coefficient of various coefficients. You can also break the periodical waveform in terms of fundamental component as well as higher harmonic components. If you forget about Fourier series, you can open your book of circuit theory to revise the concept of Fourier series once again, because it is required in case of deriving the describing function. For the time being, to let you understand what is the concept behind it, I am applying here a sinusoidal input. Okay. What is my output? My output may have, as I've already said to you, that the shape of the waveform of the output from the nonlinearity depends on the type of the nonlinearity. So just for the timing, I am considering on-off type of nonlinearity, and the output of the output waveform looks like this shape. This is YT. Now thing is that you see the output waveform is square wave, but it is periodical. Now you must have known that how the square wave form, what is the truth behind square wave form? Actually, suppose you have a sine wave form, say I have a sine wave form. This is a different concept. Okay, it is required to understand the periodicity of the square wave form, but it is a different point in this case. So it's a different point. Actually, for your understanding, that's why I'm bringing this point. Suppose I have a waveform, say x1 equals to x sine omega t. Another waveform x2 equals to capital X sine 2 omega t. Another waveform x3 equals to x sine 3 omega t. What will happen if I add them all together? So the resultant waveform says xr equals to capital X is amplitude which is common, sine omega t plus sine 2 omega t plus sine 3 omega t. So initially when what is this? Basically frequency is now initially the frequency was omega, the frequency is doubled, then frequency is tripled. So if I add the three different frequencies with same amplitude, what will happen? What is the result of the waveform? If you draw the waveform in individually, this is also sinusoidal waveform, this is also sinusoidal waveform, this is also sinusoidal waveform. Only difference is that the frequency is changed. But what will happen if I add these three waveform? Initially, this waveform was sinusoidal. This is also sinusoidal, but frequency is doubled. This is also sinusoidal, the frequency is tripled. So if I add these two waveform, then the sinusoidal waveform looks like. If I add these three waveform, then the sinusoidal waveform which looks like. So if you add more frequencies, the sinusoidal shape will there will be no more sinusoidal shape. It will be look like a square wave type of shape. So on the contrary, we can say that the square wave form is basically made by adding various frequencies of sinusoidal waveform. I mean, the square wave form is found by adding various sinusoidal waveform of different frequencies. So the fundamental component in this case sine omega t, but the 2 omega t is the higher frequency component. These are called harmonics. These are called harmonics. This is second order harmonics, the third order harmonics. If you add 4 omega t is fourth order, fourth harmonic, not order, fourth harmonic. And if you add 5 omega t is fifth harmonic. So yeah, if you add up to nth omega t is the nth harmonic. So the pure square wave form is found by adding a number of harmonic component with the fundamental component. Are you getting my point? The square wave form is found by adding various frequency component which are called harmonic component with the fundamental component. So the beauty of Fourier series is that see, when you studied Fourier series in circuit theory, when you studied Laplace transform in circuit theory, you studied the theories of Fourier and Laplace. But here you are basically you are applying the theories practically. So this concept of harmonics and not harmonics, what I want to say is that the square wave form, this concept of square wave form is basically used to find out the describing function by applying Fourier series. So what is that? What I want to say is that why should we use Fourier series? Why should I apply Fourier series? If you apply Fourier series to the square wave form, then you will have fundamental component as well as the harmonic component. In this case, if you keep only fundamental component, now if you're, as I've said to you already, that the square wave form may not be a square wave form, it may be a triangular wave form, but must be periodical. It depends, the shape of the waveform depends on the type of nonlinearities, but you can apply your Fourier series to any periodical waveform. Only you have to check that odd wave symmetry or even wave symmetry or any kind of symmetry is there or not in the waveforms to apply Fourier series and to get Fourier constants. But the point is that if you apply Fourier series to the square wave form, you can find out the fundamental component as well as the harmonic component. Now we have to make the assumption of the Deschian function says that you have to eliminate the harmonic component. You only have to keep the fundamental component, because this is the ratio between output by input. This is the complex ratio between output by input. So if the input is sinusoidal, which is x sine omega t, the output for the output we must have to keep the fundamental component. Otherwise, you can if you keep all the higher harmonic components, it is not possible to find out this kind of function. So if I apply Fourier series, that means output waveform in terms of Fourier series, I can write down the output waveform yt is equals to so a1 cos omega t, b1 sin omega t is about the fundamental component, and a0 is a DC component, and a2 cos omega t plus b2 sin omega t plus a3 sin t omega t plus b3 sin omega t is the higher third component, third harmonic component, fourth harmonic component, and so on. So what is n? The definition of n says that n, which is the Deschian function, n is y1 by x at the angle of phi 1. So what is x? You see, you have checked that x is the amplitude of the input sinusoid. What is y1? y1 is the amplitude of the fundamental component of the output. And what about phi 1? Phi 1 is the phase shift of the fundamental component of the output with respect to input. Now let's have a very closer look on this. So what is the definition of Deschian function? A Deschian function is a ratio between the fundamental component, the amplitude of the fundamental component of the output to the to the amplitude of the input, and phi 1 is the phase difference between the output fundamental component and the input sinusoid. Now, as I have explained to you that input is always sinusoidal for deriving the Deschian function. The output waveform is periodical. Maybe the shape of the waveform, periodical waveform depends on the type of the nonlinearity. And if you apply Fourier series, the Fourier series will help you to break the square waveform in terms of fundamental DC component plus the fundamental component plus the harmonic components. Now we have to keep only the fundamental component. We have to omit the DC component as well as the higher harmonic component. Okay, so we have to keep the fundamental component to derive the describing function according to the definition. Now, if since it is a1 cos omega t plus b1 sin omega t, then I can also write down the definition. What is y1 in this case? Then y1 I can say okay. Let me derive what is y1. Y1 is the fundamental amplitude of the fundamental component of the output, and x is the amplitude of the input sinusoid. Now let's have a very closer look on this. So yt is the output of the nonlinearity. So I can write down yt as a0, which is the DC component, plus within sigma n equals to 1 to infinity an cos omega t an cos n omega t plus b suffix n sin n omega t. Now n is the number of harmonic component, a1 cos, like a1 cos omega t, b1 sin omega t, then a2 cos omega 2t plus b2 sin 2 omega t plus a3 sin 3 cos 3 omega t plus b3 sin 3 omega t, and so on. Now according to the definition of describing function, we have to keep only the fundamental component. So keeping the DC component with the fundamental component, we have to keep only a1 cos omega t plus b1 sin omega t. Is it all right? Now cos omega t and sin omega t, the fundamental component comprises of cos component and sin component. Let me draw a figure for your understanding. All right? Say r theta, r at the angle of theta. You can break this r at the angle of theta in terms of r cos theta plus j r sin theta. R at the angle of theta you can write down as a r cos theta plus j r sin theta. Now sinusoidal signal starts, if the sinusoidal signal starts from the 0, time equals to 0, then the cos component will lead. That means so this is the cos component, this is the sin component. The red color is the cos component and the black color is the sin component. So cos at starting, when time equals to 0, I can write down that a0 plus a1, the cos omega t at starting is 90 degree. So a1 cos 90 degree plus b1 at starting it is 0, b1 at the angle 0 degree, not cos 90 degree, it's angle 90 degree. And at starting the angle was 90 degree as a r theta. Okay, now again a1 90 degree as a r theta, what I can do, what I can write, I can write a0. You can break this r theta as r cos theta plus a j r sin theta. So if you have a1 at the angle 90 degree, you can write a1 cos 90 degree plus j a1 sin 90 degree for this component. And what about this component? So same. So b1 cos 0 degree plus j b1 sin 0 degree. So this and thus you have a0 plus 1j, so 90 sin 90 degrees 1, so j a1 and cos 0 degree 1, so b1. If I do not consider the DC component, then I can write down yt is equals to j a1 b1 plus j a1. Now what is the magnitude of yt? So it's a plus jb form, so it will be root over a square plus a1 square plus b1 square. And what is the angle of yt? Tan inverse a1 by b1. Now what is yt? Yt is the yt is the output of the nonlinearity. So now your definition is ready. Now your definition is ready. N is the Describing function, which is the ratio between output by input, that amplitude of the output to the input sinusoid. So amplitude of the input output of the fundamental component means is a1 square plus b1 square, because Describing function requires only the fundamental component. That's why we have to keep a1 cos omega t plus b1 sin omega t. And the amplitude of the input sinusoid is given to you already, x, capital X, so it is x. And the phase difference between them is, suppose the phase initial, if the phase angle of the input sinusoid is 0 degree, and yt is found to be tan inverse a1 by b1, then the angle is this angle is tan inverse a1 by b1. So this is the derivation of Describing function. Now from Fourier series, what is a1? What is the value of a1? And what is the value of b1? a1 is nothing but 1 by pi integration 0 to 2 pi yt cos omega t d omega t, and b1 is another constant which is 0 to 2 pi, in between integration 0 to 2 pi yt sin omega t d omega t. So for any kind of nonlinearity, if you are able to find out a1 and b1, question is that how to find out a1 and b1. I will show you that how to find out a1 and b1. This is the formula for a1 and b1. You can check in the Fourier series chapter. If you are able to find out the value of a1 and b1, and if x is given to you, you can find out this ratio root over a1 square plus b1 square by x. Only you have to do, you have to find out a1 and b1. This is the most important task. If you have to find out the value of a1 and b1. I repeat, you have to find out the value of a1 and b1. If you are able to find out the value of a1 and b1, you can find out the square root of a1 square plus b1 square, and you also have already have x. So the ratio between root over a1 square plus b1 square by x is very easy to find out. And if you also have a1 and b1, you can also find out the tan inverse a1 and b1. So describing function, derivation of describing function is completely depending on the deriving of a1 and b1. And deriving of a1 and b1 requires the type of it depends on the signal yt, because deriving of a1 and b1 depends on yt is the what is yt. Otherwise, is a formula. What is yt? What is not given to you is yt. Yt is the output waveform of the nonlinear element. Now, as I have said to you already, that output waveform of the nonlinear element. In this case, I have taken the example of square waveform. But how do you know that? How do you make sure that it is square waveform or triangular waveform or trapezoidal waveform? It must be periodical. It depends on, as I have already explained to you, that it depends on the type of nonlinearity. But even if give you a saturation nonlinearity, and if I ask you to find out that what kind of wave shape of the saturation nonlinearity, if you have a sinusoidal waveform, then how do you draw? There must be a technique. What the technique I am going to in the next video I am going to discuss and explain the technique, that how to draw, how to get the various types of wave shape for depending on the type of nonlinearity, and then how to find out the value of a1 and b1, and then how to find out the discrete function. I will take the first case, a very simple case of on-off nonlinearity to explain, and then I will take another example for discussing to derive the discrete function.